Hi dear students, welcome to Gita's classes. In this class we are going to see the Laplace transform of unit step function, special function called unit step function, and we are going to see the second shifting theorem. So before that, in the previous classes I have explained all these formulas and the derivation also, all the theorems, first shifting theorem, multiplication by Laplace transform of functions which are multiplied by t power n, and how to find out the Laplace transform of the function divided by t squared, etc. And Laplace transform of derivatives, integrals and periodic function, everything I have explained in the previous classes, and try to be thorough with these formulas so that it will be useful for our next inverse Laplace transform also. Okay. So now we are going to see the Laplace transform of unit step function. Before that, what do you mean by unit step function? So the definition is given by u of t minus a is equal to 0 for t less than a and 1 for t greater than or equal to a. The graph will be like this. Suppose this is t and f of t. Then up to the point a it is 0. This is the point a, it is 0. Okay, 0 to a it will be 0. That is less than a it is 0. And from this point here, suppose if you have 1, 2, etc. Here from this point it is, for all the points it is 1. So this is the unit step function. The graph will be like this. Okay, up to less than a it is 0. From a it is the value of the function is defined as 1. So this is called unit step function, and a is always positive, that is we are going to take it the right hand side only. And Laplace transform of u of t minus a. So L of, by definition, L of u of t minus a is equal to integral 0 to infinity e power minus st f of t. Here it is u of t minus a dt, right? So what is the function here? U of t minus a is equal to, it is 0 if t less than a and 1 if t is greater than or equal to a. So from 0 to a it is, less than a it is 0, and we want from 0 to infinity. So 0 to a it is 0 and a to infinity it is 1. Okay, so we are going to divide this integral to integral as 0 to a e power minus st. In this interval, what is u of t minus a? 0. So dt plus integral a to infinity e power minus st into u of t minus a is defined as 1 into dt. So this will be 0. So only the second integral, that is e power, now you have to integrate with respect to t. So e power minus st by minus s from a to infinity. That is minus 1 by s. I am taking this minus 1 by s outside, and e power minus infinity minus e power minus as. In the place of t I am substituting e. So e power minus infinity is 0 and minus minus plus, so 1 by s into e power minus as. Therefore L of u of t minus a is equal to e power minus as by s. This is the formula. This is the Laplace transform of the unit step function. Okay, and we have some important note, that is, if the product, if you want to find out the product of the function f of t, any function f of t with u of t minus a, that is the unit step function, then it is given by, actually sometimes we will write 0 if t less than a and 1 if t greater than or equal to a, or you can write t greater than or equal to a first. Sometimes it will be given like this, that's why I have written like this. Okay, so both are accepted, both are same only. So f of t for t greater than or equal to a, 0 for t less than a. And if a is equal to 0, then the unit step function will be u of a is equal to 0. So u of t minus 0. So u of t, and this will be 1 if t greater than, a is equal to 0. So 1 if t greater than or equal to 0, 0 if t is less than 0. Okay. Now second shifting theorem. So second shifting theorem says that if L of f of t is equal to f bar of s, then L of f of t minus a into u of t minus a is equal to e power minus as into f bar of s. This theorem will be of great use for finding the inverse Laplace transform also. Okay. And if the function is of the form f of t minus a into u of t minus a. U of t minus a is what? Unit step function. Okay. Then e power minus as into L of f of t. Actually, this function is u of f of t minus a. And for f of t, you have to find out L of f of t. That is our f bar of s. And e power minus as should be multiplied by this. Okay, first let us prove the theorem. L of f of t minus a into u of t minus a is equal to, by definition it is integral 0 to infinity e power minus st f of t minus a into u of t minus a into dt, right? What is the function f of t minus a into u of t minus a is equal to 0 if t is less than a and f of t minus a if t is greater than or equal to a, right? So this L of f of t minus a into u of t minus a is equal to integral 0 to a e power minus st into f of t minus a into u of t minus a dt, or you can directly write in this interval it is defined as 0. So 0 into dt plus integral a to infinity. Here it is defined as f of t minus a into dt, right? So this will become 0. Therefore it is integral a to infinity e power minus st f of t minus a dt. Now you put t minus a is equal to another variable u. Okay. T minus a is equal to, whenever you are substituting the variable, you have to do three more things. One is dt. Dt is equal to du. And when t is equal to a, what will be the value of u? T is equal to a. So a minus a. Okay. So a minus a, which is 0. When t is equal to infinity, u is also infinity. Therefore, this integral becomes integral a 0 to infinity. A will become 0. E power minus s of, here t minus a is equal to u, implies t is equal to u plus a, right? So s into u plus a into f of u into du, right? So this is equal to integral 0 to infinity e power minus su e power minus as f of u du. So the differential integral is with respect to the variable u. So e power minus as is independent of that. So I can take that outside. So e power minus as into integral 0 to infinity. See e power, okay, I'll write again, e power minus su into f of u du. This can also be written as e power minus as into integral 0 to infinity e power minus st f of t dt. See, here the variable is called dummy variable because here with respect to the variable u, you are integrating and substituting the limits from 0 to infinity. So after that u will not be there. So in the place of whether u, whether I write u or t or any other variable x or y, it doesn't matter, because after that we are going to substitute the variables, okay, substitute the values, limits for the variable, so that variables will not be there after integration. After substituting the limits, that variable will not be there. So it is called a dummy variable. So instead of u, I am writing t. Okay. So this is equal to e power minus as into, what is this? L of f of t. By definition, it is L of f of t. Or you can write e power minus as into f bar of s. Therefore, L of f of t minus a into u of t minus a is equal to e power minus as into f bar of s. That is, for this f of t minus a, you find out f of t, and find the Laplace transform of f of t. That will be our f bar of s, and just multiply by e power minus as. Let us do some problems on that. Find the Laplace transform of the function g of t, where g of t is equal to cos of t minus pi by 3 if t is greater than pi by 3, or you can say greater than or equal to pi by 3 also, and 0 if t is less than pi by 3. Okay. So now we have to compare this with our function. So g of t is equal to, instead of f of t minus pi by 3, I am writing this as cos of t minus pi by 3. If t is greater than or equal to pi by 3, and 0 if t is less than pi by 3. Okay. So here what is our f of t then? Cos t. F of t minus pi by 3 is cos of t minus pi by 3. So f of t is cos t. This implies L of f of t is equal to, or f bar of s is equal to L of f of t, which is equal to L of cos t, which is our s by s squared plus 1. So f bar of s is equal to s by s squared plus 1. So if you want to find out we want to find out the Laplace transform of g of t, right? So L of g of t is equal to e power minus, according to, by using second shifting theorem. You can write by second shifting theorem. Actually this can be written as u of f of t minus 3 into u of f of t minus pi by 3 into u of t minus pi by 3. That is our function, right? So L of g of t is equal to e power minus as into f bar of s. Here what is our a? Where a is equal to pi by 3. Okay. So this is equal to e power minus pi by 3s into f bar of s is what? S by s squared plus 1. So s by s into e power minus pi s by 3 divided by s squared plus 1 is our Laplace transform of the required function. Okay. We'll do one more problem. Find the Laplace transform of t minus 2 the whole cube into u of t minus 2. So in the previous problem they have given like this. Cos of t minus pi by 3. That is, by this definition you can compare this with this function f of t minus a is into u of t minus a. Here f of t, the function was given like this. Okay, f of t minus a. G of t is given like this. Cos of t minus pi by 3. Now t minus 2 the whole cube into u of, find the Laplace transform of L of t minus 2 the whole cube into u of t minus 2, right? So here f of t minus 2 is equal to t minus 2 the whole cube, right? Here what is our a? Is equal to 2. So what is our f of t? It is t cube. In the place of t minus 2, just replace it by t. So f of t is equal to t cube means L of f of t, that is our f bar of s, is equal to L of t cube, right? So that is 3 factorial by s power 4 or 6 by s power 4. Therefore, L of t minus 2 the whole cube into u of t minus 2 is equal to, by using second shifting theorem, e power minus as into f bar of s, where a is equal to 2 and f bar of s is 6 by s power 4. Therefore, by second shifting theorem, we get L of t minus 2 the whole cube into u of t minus 2 is equal to e power minus as. So e power minus 2s into 6 by s power 4. 6 by s power 4 is the answer. Or you can write 6 into e power minus 2s divided by s power 4 also you can write. Next question. Find L of e power minus 3t into u of t minus 2 by using second shifting theorem. So if you want to use second shifting theorem, always the function should be of this form. F of t minus a into u of t minus a. So here u of t minus 2 is there. So e power minus 3t can be, you have to represent this as a function of t minus 2. So I can write it as e power minus of, I want t minus 2, right? So what is left out here? E power minus 3t is only available. So this is equal to e power minus 3t plus 6. That is e power minus 3t into e power 6. It is available. This is only required, but we have only e power minus 3t is available. So multiply and divide by e power 6 and e power minus 6. So here add and subtract 6. Okay. So minus 6. Add 6. Actually minus 3t plus 6 minus 6. Minus 3t plus 6 minus 6. This is equal to, into u of t minus 2 you can write, of course, is equal to e power minus, from these two terms I am taking minus 3 outside so that it will become t minus 2. Are you getting minus 3t? Minus 3 into minus 2, it will be plus 6. Okay. And into e power minus 6 into u of t minus 2. So L of, you want to find out the Laplace transform of e power minus 3t into u of t minus 2 is equal to e power minus 6. L of, you write all these things, then you minus 3 into t minus 2 e power minus 6 into u of t minus 2. So I can take this e power minus 6 outside because it is just a number. So L of e power minus 3 into t minus 2 into u of t minus 2. So this is equal to, now this is L of some function of t minus 2 into u of t minus 2. Therefore f of t minus 2, f of t minus 2 is equal to e power minus 3 into t minus 2. This implies f of t is equal to e power minus 3t. So if f of t is equal to e power minus 3t, then f bar of s is equal to L of f of t, that is L of e power minus 3t, which is 1 by s plus 3, right? Therefore, by second shifting theorem, we are going to apply, we want this one. So therefore, by second shifting theorem, how will you apply second shifting theorem? L of e power minus 3t into u of t minus 2. This is what we want. It is equal to e power minus 6 into e power minus 6 only, no? E power minus 6 into e power, here what is our a? A is equal to 2. Okay, from this given values, a is equal to 2. This is given value. Okay. So e power minus 6 into e power minus as. Actually, first you write this value, e power minus 6 into e power minus as into f bar of s. Okay, by using second shifting theorem. So e power minus 6 into e power minus 2s into f bar of s is 1 by s plus 3. Right? And here you can combine these two. So e power minus 2 into s plus 3. Right? E power minus 2s, e power minus 6 divided by s plus 3. This is the answer. But here in the question they have mentioned by using second shifting theorem. Otherwise also you can use first shifting theorem. Do you know this? L of e power minus 3t. Actually, if it is mentioned in the exam by using second shifting theorem, then you have to use this method only. You have to make the adjustments for making this e power minus 3t as function of t minus 2. Otherwise, you can use first shifting theorem also. E power minus 3t into u of t minus 2, which is equal to L of u of t minus 2, in which s should be replaced by s plus 3. Right? This is, what is L of e power, L of u of t minus 2? E power minus as by s, right? Here a is equal to 2 again. A is equal to 2 given. So e power minus 2s by s, in which s should be replaced by s plus 3. That is equal to e power minus 2 of, wherever you have s, it should be replaced by s plus 3 divided by s plus 3. So this is what we had, no? E power minus 2 into, this is our answer in the previous method. By using the previous method, this is the answer. And the same thing we got, e power minus 2 by using first shifting theorem. Here by using first shifting theorem. So if it is not mentioned, this is easier. Using the first shifting theorem is easier. But in the problem it is mentioned that by using second shifting theorem, then you have to make the adjustments accordingly. Okay. And please share it with your friends also. Give a like for this class. And please share it with your friends so that it will be useful for them. And thank you so much for listening.